I'm really pleased to be able to introduce Dr. Dana Qasim. Um, we're part of the Night Sky Network, and every year are you able to hear me? All right, everybody. Every year, they give us an opportunity to request speakers, and we reached out, and they came back and suggested that we contact Dr. Qasim. And I'm really excited to hear what she has to tell us about unlocking the chemistry of the heavens. I think I'm serious. It's kind of a cool thing for me. I'm hope for a lot of other folks. And just in a way of introduction, Dr. Qasim is a laboratory astrophysicist and astronomer, and her long-term goal is bridging interstellar and protoplanetary disk chemistry to the chemistry of our solar system. In other words, we've got all of these data in different areas. We need to be able to pull them all together to really understand what's going on. And Dr. Qasim received her Bachelor of Science in Chemistry and minor in astronomy at Northern Arizona University, and her Master of Science in Chemical Sciences at Kennesaw State University under the supervision of Professor Heather Abbott Lyon, where she received her PhD in astronomy at Leiden University under the supervision of Professor Harold Linnartz and Weenie van Dashik in 2020. Notably, she developed a method to experimentally investigate carbon atom chemistry occurring in dark interstellar clouds, which resulted in 2 international dissertation awards. After her PhD, she did postdoctoral work at NASA Goddard Space Flight
Oh, got it. Okay.
where she worked in the cosmic ice and astrobiology analytical laboratories to bridge interstellar chemistry to the chemistry found in meteorites. In 2022, she joined Southwest Research Institute's planetary science research staff, where she is currently leading a James Webb Space Telescope Cycle 3 program on interstellar sulfur chemistry, a NASA New Frontiers data analysis program on analyzing Juno data of Ganymede, and is head of the newly formed Nebular Origins of the Universe Research Laboratory, NOUR Laboratory, and she made sure I understood that NOR also is the word for light in Aramaic. So with that, I will be very pleased to turn the meeting over to Dr. Dana Qasim.
Thanks, Don. And thank you.
One thing before, I'm sorry to interrupt you. One thing I forgot. If you have questions and if you want to ask them by politely interrupting Dr. Qasim, please raise your virtual hand and we'll try and recognize you. But you also can put them in the group chat, and at the end of the presentation, we'll ask you to have your questions asked at that point as well if you put them in the chat. Sorry. Go ahead, Dr. Qasim. I'm sorry for the interruption.
No problem. Yeah, I like questions during the talk too. It kind of feels a bit more natural or organic. So please don't hesitate if you have any questions. Okay, so I'm Dana. Just feel free to call me Dana. So I'm at Southwest Research Institute in San Antonio, Texas, and I was super excited to get an email saying that I could give a talk to the Houston Astronomical Society. I'm pretty new to Texas. I moved here just a couple years ago, so it's a good way to know my neighbors. I don't think I've ever been to Houston. I don't remember. So anyways, I'm really honored to be here. And so I'm going to give a talk about my astrochemical journey. So I'm an astrochemist, and I'm going to talk a little bit about what an astrochemist is. And I'm going to talk about basically what I've been doing, my research journey from high school. So I started this line of work when I was 16, at the young age of 16, and now I'm 35. And I'll talk about the research that I've been doing and what I'm doing today. And most importantly, I'm going to just briefly touch on the dire funding climate for NASA and what all of you can do to help us during this time. And so this talk is called Unlocking the Chemistry of the Heavens, and it's in dedication to my late PhD supervisor, Professor Harold Linnartz. He passed away unexpectedly December 31st, 2023, and I coincidentally got sick all of 2024, so I wasn't able to give a talk in dedication to him. So this is the talk that I dedicate to his memory. And just a little bit of a warning, I am a chemist, so there's a lot of chemistry in this talk, but it's a fun time, and I'm excited to share what astrochemistry is like, because I think it's not as popular as maybe like astrophysics, and this is uh, yeah, it'll be a good time. But the most important thing, and if there's anything that you take away from this talk, is I hope it's this slide here. So the president proposed a budget to NASA, and it just hit Congress to slash NASA's science budget in half, so 47% the NASA science budget, which gives me goosebumps because it's quite scary. So the budget cut would basically have NASA financially at a place where the funding level is in the 1960s. So you can imagine, like, if your salary is now the salary of living in the 1960s, but you're in 2025, that's really hard to survive. And so
notice we're still seeing the title slide.
The president's budget is asking to slash NASA's funding in half, and so this image over here, you can see all these red crosses, and it's basically all the NASA missions that would go down if this budget were to pass, and or this proposal were to pass. And so there are a lot of beautiful missions out there that are running really well and collecting beautiful data, and yeah, jobs are already being lost, grants are being terminated. So it's really dark times. And so what you can do, so Congress is ultimately, will decide to what extent this proposal will pass. And what you can do is contact your representatives and let them know, if you were ever inspired by an image from NASA, please click on these links, just take a screenshot or something. And there's a form. The form is very simple. It only takes a couple minutes, and there's already a template that lists everything that basically, yeah, it's a template to help you fill out the form. So please let people know around you about what's going on, and hopefully we can try to save the budget for NASA and for other science organizations as well. Okay, so how did I become an astrochemist? So an astrochemist is someone who investigates the chemistry between the stars. So I study interstellar chemistry. So inter means in between, and stellar means the stars. So it's the chemistry in between the stars. And I think that this image here is a really nice image to kind of describe what I do. So over here to the left side, you can see this is our solar system. And as you go out of our solar system, then you enter the interstellar medium. And so this interstellar medium is rich with chemicals. So we thought that this region was just empty and dark and there was nothing really going on, but it's actually this rich chemical organic chemical factory. And there's what we call the building blocks of life. So there's amines, amino acids. Amino acids make up proteins in your body. We found sugars there, carbon, long carbon chains. So anyway, so I study the interstellar medium. And so the interstellar medium has the clouds, interstellar molecular cloud. And this cloud will collapse onto itself, and the temperature goes up, the heat goes up, and our star is born. And so that our sun comes from this interstellar cloud, and then all that material revolves around our sun and becomes the planets and the moons. And so that was a very simplified version of solar system formation. But my point here is that as an astrochemist, I study the gas, dust, and ice chemistry that happens in these interstellar clouds. And I'm trying to understand, how did these building blocks of life get fed into forming our planet? And is our planet unique with having life? And did these building blocks of life also go into other solar systems, and how so? And so that's what I'm trying to do, is to make that connection between the interstellar cloud and the chemistry that we see in our solar system, and notably to interpret the data from these space missions that are studying, that are going to all these different satellites, to Jupiter, to the moon, and trying to understand what's happening on these planetary surfaces, these solar system bodies. And how does interstellar chemistry play a role into the data that we're collecting? So the way that I got into this, this whole astrochemistry ordeal, is I was in high school, and I did an internship called Women in Science and Engineering. So I shadowed a graduate student who is now, she's from Houston, and she's a project scientist for the James Webb Space Telescope. And she basically motivated me and encouraged me to study, to be an astrochemist. I never thought that you could study the stars for a living, that you could make it a career. And she encouraged me, and I just needed one person to tell me that you can. And so I went to undergrad at Northern Arizona University. So I'm from Tucson, Arizona. And I got my bachelor's in chemistry, my minor in astronomy, and I also did a couple internships. So at Arecibo Observatory, which, if you know, during COVID, the Gregorian dome fell, and Arecibo is not functioning anymore. It's given to the jungle. The jungle is eating it alive, unfortunately. And I also did an internship in Socorro, New Mexico, with the VLA. So I was very blessed, very grateful that I had these really awesome experiences that prepared me to go into graduate school to get my doctorate in astrochemistry. So I went to Emory University to do my PhD, and that did not work out. I was there for 1 year, and after 1 year, I was kicked out of the program. I was found to not be qualified for their research program, and my grades were not high enough to go into the next parts of the graduate program. But like, till this day, I mean, this is over 10 years ago, and till this day, I just think it was a very subjective evaluation, and I just thought I was better than that. So I applied to graduate schools again. But the hard part is, when you get kicked out of a graduate program, nobody wants you, because it's a red flag. It taints your record. But like, I was pretty afraid to even do a PhD program. But I applied anyways, because I felt that I should at least get a graduate degree. It would be helpful for my career, just, higher paying job. And so when I was applying, I had to also get a job. I needed to make money. So I worked at Kimberly-Clark Corporation. And they make the toilet paper. And I looked at toilet paper under a microscope for a year. And I did not enjoy looking at toilet paper, but I really liked working with the scanning electron microscope, energy dispersive spectrometer. That was a lot of fun. that's a very valuable technique, and I ended up using that technique in my master's when I started to do research all over again. So I did a master's program instead of a PhD program because PhD programs didn't want me. But also I was afraid to do a PhD. I did not have a good experience at Emory University, and I really did not want to go through something like that again. So I did a master's, and it was a really good experience for me. I worked in Kennesaw University under the supervision of Professor Heather Abbott, and we did a lot of collaboration with Georgia Tech, and I worked in this big collaboration network called the Center for Chemical Evolution. So we were trying to understand the prebiotic chemistry on the early Earth, so the origin of life on the early Earth. And yeah, it was a really great experience for me. I was actually on the route to do teaching because I thought, okay, after I leave my master's, maybe I'll like teach somewhere, because I don't know if research is good for me or if I'm good for research or good at research. But I ended up publishing 2 papers in the program, and so I guess I had confidence that, okay, I'm actually not too bad at research. So I'm going to talk a bit about my research project in my master's. So again, so we were doing the origin of life chemistry. So we're trying to understand how did life come to be on the early Earth. And the project that I specifically worked on was understanding the chemical properties, and specifically the surface of a meteoritic mineral called schreibersite. So schreibersite is made up of iron, nickel, and phosphorus. And well, I'll talk about why schreibersite was a unique mineral and how it has a role in trying to understand the origin of life on Earth. So there's a by the way, if anybody has any questions, please don't hesitate to ask. So there's a problem in the origin of life community, and it's called the phosphorus problem. And so the issue with the phosphorus issues with phosphorus is that so humans are composed of phosphorus. We're composed of about 1% phosphorus, which is actually a lot of phosphorus, for just one element. So we're composed of phosphorus. We particularly have phosphates in our body. So it's PO4. So it's 1 phosphorus and then 4 oxygens attached to it. And the issue is that phosphate in most minerals, so a lot of phosphorus is found in a solid form in minerals, in rocks. And a lot of phosphate is, so they're trapped in these minerals. And the two issues that we have with the phosphorus problem is that phosphate is not very soluble in water. So if you take, for example, this mineral here, hydroxyapatite, and you put it in water, the phosphate is not going to be easily released into the water. And a lot of chemical reactions important to the origin of life happens in water. And then even if phosphate is able to be released into water, it's not very chemically reactive. So if it's not chemically reactive, then how does it react with chemicals to be incorporated into life forms? So those are the 2 big problems. It's called the phosphorus problem in the origin of life community, which is that most of the phosphorus is in this very non-reactive molecule, yet it's very important to life. And so, for example, this is showing an image of a cell. So there's a cell membrane, and then the cell membrane is composed of this glycerophospholipid bilayer. And that bilayer has a glycerophospholipid. And then you can see here, that's where the phosphate is attached to an alcohol and a glycerol. So basically the phosphate is bonded to the alcohol and glycerol, but phosphate is not chemically reactive. So we don't understand, how did phosphate get into this phospholipid and contribute to forming cell membranes important to life. And some other problems attached to this is, so the Center for Chemical Evolution, that was the group that I was a part of, their model suggests that enzymes were not available on the early Earth. And so enzymes, as we know, they're in our bodies, and they help facilitate chemical reactions that are difficult to happen. So they can help facilitate, for example, phosphate going into a molecule and doing phosphorylation and making the glycerophospholipid. But on the early Earth, we don't think that there were enzymes that could do these processes. And also, you have to put in a lot of energy for phosphate to be incorporated into biological molecules. For example, like adenosine diphosphate, that takes a lot of energy that we don't think the early Earth had to supply. So those are the two problems, which is, how did phosphate become incorporated into life systems if it's not water soluble and it's not very chemically reactive? And so that's why we really like this mineral. It's called schreibersite. So schreibersite is proposed to be the most likely phosphorus mineral source for several reasons. I'm just going to name a couple reasons, but basically schreibersite has a reduced form of phosphorus. So it doesn't have phosphate, which is PO43-. It just has the phosphorus, just one phosphorus. And that is very reactive. It's very chemically reactive. I remember when we were in lab, even, we were playing with the mineral, and I thought I was going to die that day, because we could, you could like smell like a fish kind of smell, which is what I think phosphine smells like. And you don't want to smell phosphine. So it was reacting with the water vapor in air. So it's a very chemically reactive mineral. And there have been geochemical model studies that show that schreibersite was delivered to the early Earth during the late heavy bombardment. And so, and I really love this image here. So our collaborators at Georgia Tech, what they did was they took the schreibersite mineral and they put it in this solution that contains like uridine and adenosine and all these biologically relevant molecules, and they put it in that solution, and then they heated it just for 2 days. So after 2 days of heating, it looks like this like blood orange, like what you would think of like Origin of Life gunk. And so it was basically, the phosphorus was reacting and phosphorylating these organic molecules to form biologically bigger molecules that are important to life. So that's cool. So we did a bunch of what we call demonstration reactions, which is like, look what we can make. So we cooked up all these chemicals, but we don't understand how we're making these, like what is the chemical mechanism? Like, how is this actually happening? And an important part of all these chemical simulations, these reactions, is that the schreibersite surface is always involved. So that mineral is always in all of these reactions. You need the mineral there. And so that indicates that the surface of the mineral may actually be participating in the phosphorylation process. So the surface may be acting like as a catalyst or a platform for where the chemical reactions take place. And so that was our group. Our group was to study that. And by the way, please let me know on time, because I know I'm a little bit behind with all my hiccups with the slides. Anyway, so my group, or my professor's group, we studied how does the mineral surface participate in the phosphorylation mechanism? And that's something that I am going to continue doing in now my actual lab. My master's supervisor is retiring, and I actually just took some of her equipment, and it's going into my laboratory right now. And so I'm going to be chasing this problem that I guess abandoned after I left. So 11 years later. So we try to understand how does the mineral surface participate in the mechanism, and so the way we did this was to just try to characterize the surface first before going into the more interesting experiments, which is to actually put the mineral in like a liquid solution and trying to understand the surface, how the surface chemistry is participating in this phosphorylation mechanism. We can't do that because that's too advanced. So we start from ground zero, which is what is the surface? What is it like? And we were trying to characterize the surface itself. And so that's where, so I published 2 papers on that. Yeah, so the left side shows a spectrum of, so what I did was I put water. So I worked in an ultra high vacuum system. So ultra high vacuum is very low pressure. It's, I don't know how to convert units into like atmospheres, but it's 10 to the minus 10 torr. So basically we're kicking out molecules and atoms out of the air. And the reason why we do that is because we want to just study the interface, the chemistry that's happening at the mineral surface and whatever molecule we put on top of the surface. And so we put water because water is the medium at which all these chemical, like origin of life chemical reactions take place. And so we put water on top of the schreibersite surface. And so the left side, you can see there's this pink spectrum here, and this shows water onto schreibersite at a very low temperature of 130 Kelvin. I don't know how to convert that to Fahrenheit or Celsius, but it's very cold. And then when we heated it up to room temperature, we see in the infrared that there's a dip that forms, this huge dip. And then I did the experiment again without phosphorus. So it's just iron and nickel, and there's no phosphorus. And so what that tells me is that the iron nickel phosphide, and particularly the phosphorus, reacted with the water to make some sort of phosphorus bearing species. And in 2022, so I did these experiments, I published this paper, I think in like 2016 or something. And then in 2022, this group in Italy did computational studies on our experiments, and they confirmed that this is representative of the formation of, I think, phosphonic acid. So this is really interesting and very cool because it shows that the chemistry is happening right on the surface. It's not just happening in the aqueous, like that blood red solution. It's not just happening all in the liquid phase. The surface is actually doing some chemistry itself because it's happening right on the surface. So, that's one key or one piece of the puzzle to the mechanism. And then I did scanning electron microscopy of the minerals, which I learned at Kimberly-Clark. So all that, the toilet paper analysis days came to good use. And I looked at, so scanning electron microscopy was basically I zoomed in on the mineral, and then I put elemental maps on top of the mineral, the topography. And so I looked at the distribution of iron on the mineral, the distribution of nickel, and the distribution of phosphorus. And you can see that one of them is not like the rest. Phosphorus is a weirdo. So you can see that it has these like black voids. And so this image here, this is a secondary electron image of the mineral. And then here, the blue shows the distribution of phosphorus. And you can see that the phosphorus is particularly located at these brighter sites. And these brighter sites are edges. So they're like little cliffs on the mineral. And then these darker regions they're more flat. And so what that indicates is that the phosphorus segregated onto these edges. And what's interesting about that, the fact that they are segregated, is that edges, or what we call our defect sites, they are catalytic, so they promote chemical reactions more than these flat terrace sites. And so that is also another indication that the structure of the surface itself may be contributing to the phosphorylation process. And this was something totally unexpected. We didn't think, I just thought, okay, I'm just going to take some nice images to see what it looks like under the microscope. And I was pretty surprised that the phosphorus had segregated to these catalytic sites. So basically, conclusions on the schreibersite study to the best of my knowledge, I think we were the only group that was studying the surface in that particular manner. And so 10 years, it's been over 10 years. I don't think there has been a continuation on this. And so I'm very excited to continue working on this project. It was like my baby. It's like my first research project, and it was so exciting. And I think that there's so much to uncover. And so I would like to repeat these experiments. I would like to put them not in a vacuum, but to actually put the mineral in an aqueous liquid solution to mimic more of the origin of life chemistry, and try to understand the dynamics happening at that interface, and try to better understand how the surface is contributing to the phosphorylation, origin of life chemical reactions. And what's also really cool about this is that we did see some of these chemical reactions happening at low temperatures, so temperatures relevant to space. And so that's indicating that there may be this schreibersite phosphorus chemistry happening not just on Earth, but could be happening in asteroids. Schreibersite is meteoritic for the most part, so it comes from an asteroid. So we could be having this phosphorylation chemistry that happens in our bodies happening on these asteroids, and maybe just being distributed out to other to moons and planets. So so that's something that I'd like to follow up on, is how schreibersite chemistry is happening in asteroids and other solar system bodies. Okay, so let me just check. Oh, I have like 5 minutes left. Well, I'm just gonna zoom through this. So I did my PhD in astronomy.
You've got more time than that. I mean, we were a little bit behind. So if you want to take 20 minutes, 25 minutes, that's fine.
Okay, thanks. I'll do like just 20 minutes. I don't want to take up everyone's Friday night. But thank you. So I did so I finished my master's, and I was very afraid to do a PhD in the US after my experience at Emory, and I was looking for a job in industry, more on the research side, because I did like research way more than teaching. But then someone, actually Stephanie, the person that I mentored, she was my mentor back in high school, she sent me this link where they were looking for a PhD student at Leiden University in the Netherlands. And Leiden is Leiden is where astrochemistry started. And Leiden is very famous for a lot of the notable scientific figures. Albert Einstein was a visiting scholar there. We have van der Waals. It's really, it was very humbling to be there. And anyway, so they were looking for a PhD student, and the description was exactly my background in my master's. And I was like, oh my gosh, I don't know if I want to do this all over again, and now in a foreign country. Like, what if I get kicked out and I'm in a foreign country? What, like, just sounded like a nightmare to me. But I applied, and I had the interview with Harold, and it went really well. And then so it convinced me to go to the Netherlands. And I don't know, I was fine to leave Georgia. So these are some pictures that I had from the Netherlands. There's no filter. These are pictures from my house when I was there. And it was a really beautiful 4 years there. So I studied in the Netherlands. My PhD project was to study the dense cloud. So this dense interstellar cloud. So the dense interstellar cloud is where the first icy organics are formed. So water, for example, water that we drink, that water is initially formed in the dense interstellar cloud by adding hydrogen atoms to oxygen. And so that's what I studied, was the formation of the very first molecules in space. So water, methane, ammonia, all these little building blocks of more complex organics, and then there's more complex organics that are formed. And so I was making molecules out of atoms. So I worked with atom beamlines, and I actually built this one here. This was part of my PhD project. And I graduated just a year before James Webb came out. So that was really, exciting. So I'm just going to talk about this paper that I published. It was in Nature Astronomy. I was super excited about it, and it's basically forming methane in interstellar molecular clouds. So it starts off, so in interstellar clouds, there are different phases of how an interstellar cloud comes to be. So in the very beginning, there's a phase called the translucent cloud phase, and it's mostly water-rich ices. And there's a lot of atoms like carbon, nitrogen, oxygen. They're all in the gas phase, and they come down onto these cold grains, and they start reacting with each other, and they start forming water. They start forming ammonia, start forming methane. And then as that cloud evolves over time, it starts to become more dense. The dust and the gas start to accumulate, and it starts to get more dense, and it gets to become more cold. The temperature drops, and now there's a lot of carbon monoxide that's in the gas phase, and that carbon monoxide will then eventually hit the surface of these dust grains, and carbon monoxide can get hydrogenated to form more complex organics like methanol, glycolaldehyde, ethylene glycol, and like these bigger molecules that become more complex and become more biologically relevant. So it's a lot of rich chemistry happening in these clouds, and that black region eventually will become our star, turn into a star. So again, why do we even care about understanding this dense cloud chemistry? Well, this dense cloud chemistry, these molecules could have been incorporated into forming planets, and they are incorporated into forming planets and our moons and asteroids and comets, and we're still trying to understand exactly how that is. And James Webb has helped a lot with that. James Webb has provided the golden age, golden era for astrochemistry. And so some of these questions that we have still is trying to understand, like, what fraction of the molecules are inherited by the protoplanetary disk. So that's the next phase. So after that cloud comes and forms the star, there's that disk. And that protoplanetary disk is when the planets are really starting to take shape, and that's where comets and asteroids are formed. So how much of that is inherited by the cloud? And then the big $1 million question is, how important are these molecules to the chemistry that's happening on the early Earth? So these are the most abundant ices that have been detected in interstellar clouds. So it's water, carbon dioxide, carbon monoxide, methanol, ammonia, and methane. And so we know water. So in the literature, we know water is formed by adding hydrogen atoms to oxygen. Carbon dioxide is formed by this chemical reaction of carbon monoxide with OH. Carbon monoxide is a gas phase molecule. Methanol, you just take hydrogen, add it to carbon monoxide, and you make methanol. And ammonia, you add hydrogen to nitrogen. Methane was a mystery. In models, they say that you should add hydrogen to carbon, and then you just make methane. But no one ever proved it. There has been no experiment, no proof that showed that if you add hydrogen atoms to carbon, you will make methane. And this has been in models for like I don't know, as long as astrochemistry has been alive, so maybe like 100 years or something. And there are a couple experiments that did happen before that studied formation of methane, but some of the chemical reactions are questionable, and it was at a time where like there just wasn't as much technology. Like there's a limitation on technology, and so there's a limitation on what you could uncover in your experiments. And so that was a huge part of my thesis, was to form methane. It's a very simple, it sounds very simple, but it was important because methane is one of the most abundant ices in interstellar clouds. And so if it's very abundant in the interstellar cloud, it's going to be largely incorporated into forming planets and moons. And we need to have numbers behind methane formation. We need to understand how it's formed, and is it actually formed by adding hydrogen to carbon atoms. And so we did it with this beautiful setup called supervisor. And these are different atom beam lines. So this one shoots carbon atoms onto a substrate that's cooled to 10 Kelvin, so super low temperatures. This one shoots out hydrogen, and this one shoots out nitrogen and oxygen atoms, and there's no radiation. And so that's what's so beautiful about this too, is people think that, okay, in these very low temperature clouds, like how can you have any chemical reactions happening if the temperatures are super low? So people thought, okay, it's radiation. Like radiation is inducing all this chemistry, but actually you don't even need radiation. It's the fact that atoms are just very reactive, and so they're super reactive, and they'll just react with each other and make molecules. And that's just some details. And so I was talking about the beam, and these are all the details of the setup. And so I basically did two experiments I did many experiments, but they're like two different types of experiments. So one experiment is just doing carbon and hydrogen, just to see if we can make methane formed from adding hydrogen to carbon atoms. And then I did carbon plus hydrogen plus water, because that's more representative of these interstellar ice grains that have water already formed while methane is being formed. And so these are just some parameters of the experiments. And so we just studied some of the effects of how water affects methane formation. And so one of the things that I was nervous about was maybe water would be blocking hydrogen and carbon from reacting with each other to make methane. But actually what we see is that water enhances methane formation, and we see even more methane formed in the water experiments than the experiments that didn't have water ice. And so we think that water actually like keeps hydrogen in the ice longer. So the big picture of this is basically showing proof. Okay, we actually have proof that you can make methane in the way that models have predicted, which is you add hydrogen to carbon in a water ice. And now we understand how these simple hydrides are formed. And these simple hydrides can turn into bigger, more biologically relevant molecules, or they can be transferred to the next stages of star formation. So Titan, which is a moon of Saturn. Yeah, I think it's a moon of Saturn. I'm still learning the planets and the moons. There have been studies that suggest that the methane on Titan's atmosphere, on Titan is from interstellar clouds. And now we have more numbers for models, and these models will go into interpreting data from the James Webb Space Telescope. And James Webb is really great to look for methane, because you can't really look at methane with ground-based telescopes because of telluric contamination. And so having a space-based telescope like James Webb is perfect for this type of work. Okay, so after my PhD was fantastic. I loved it. Had a great 4 years. I won 2 international dissertation awards. And I say that because I just remember my humble beginnings when I got kicked out of a PhD program and had to find my way back into research, and I won best dissertation by the International Astronomical Union and the American Chemical Society. So I felt really good. And so I went to NASA Goddard to do my postdoc, and that was really successful too. NASA media really liked the project that I was working on, which is understanding. That's when I started to make the bridge between interstellar chemistry and the chemistry that's important to life in our solar system and on Earth. So I'm just going to briefly talk about that. So I was talking about this dark cloud chemistry, right? We make these simple molecules like water and carbon dioxide and ammonia. And then when these icy grains, they eventually get transferred to the next stages of star formation. So in the protostellar phase, so that's when the violent star is born, and there's just chaos. And so there's tons of radiation. That radiation will form methylamine and alanine and amino acids and amines, and then that will get incorporated into those dust grains, icy grains. They start to come together and stick together, and you start making asteroids. And asteroids contain even bigger, more complex molecules. And so and actually the water on these asteroids, it starts as a water ice, but then there are radioactive nuclides that heat up that water ice and form a liquid. And so you actually have liquids in space, which I didn't know until I did my postdoc. So I have to study liquid chemistry on asteroids. So that's what I did. And so I worked with the Van de Graaff accelerator. So that was to simulate cosmic ray chemistry. So it shot out 1 MeV protons, which is very high energy protons that make up cosmic rays. And I would irradiate these ices with the Van de Graaff accelerator to make these residues that contain these biologically relevant molecules. And then I would go into the astrobiology laboratory, and this isn't their laboratory, but members of the laboratory were part of the OSIRIS-REx mission. So some of you may know the OSIRIS-REx mission collected samples from Bennu, and people are working on that right now. And but hopefully the OSIRIS-REx mission is on the chopping block for the budget. So if you like the OSIRIS-REx mission, tell your representative to keep it. So I guess some of the highlights with the experiments is, well, I'll just say my favorite highlight. My favorite highlight is that we actually saw salts in the experiments. So I knew that I was going to form amines in my experiments, but I knew the amines would disappear by the time I would do the astrobiological processing, the asteroid processing of these molecules. But the amines did not disappear. They actually were the most abundant species, more abundant than the amino acids. And we saw that there were salts also in my experiments. And so that suggests that these volatile species can be trapped. Volatile species from the interstellar cloud can be trapped in salts and can be preserved in these salts as they make their way into the solar system. And our solar system is pretty salty. Comet 67P has a lot of salts. Comets are very salty. And so a lot of these salts could actually be containing this interstellar material. And so there's more interstellar inheritance than I think we realize. And it's definitely an exciting research path for myself. And now I'm at Southwest Research Institute. So I did my postdoc for 2 years, and then I got a full-time job at Southwest Research in San Antonio. So I'm a senior research scientist there. And this is my supervisor's lab, Center for Laboratory Astrophysics and Space Science Experiments. If any of you ever want to come to San Antonio and come visit, we do tours here. I think it's great to show we're a nonprofit organization, so it's great to show people, what we're doing here, and then share our passion to everybody. And so we study a lot of chemistry and physics of mostly the solar system, trying to understand like surface exosphere dynamics, and we use all these ultra high vacuum chambers. These two chambers are pretty cool because we work with Apollo samples. So we actually have samples from the Apollo mission, lunar samples, in a safe, and we put them in these vacuum systems, and we try to understand the properties of these lunar soils. And I just got my own lab last month. And so my role is to actually understand all the solar system chemistry from a nebular origins perspective, right? Of how interstellar chemistry contributes to solar system chemistry. And it's called the NOUR Laboratory. NOUR is light in Arabic, which I find very fitting because a lot of stars have their names are of Arab origin. And so we're creating this laboratory. It's super exciting. It's a lot of work and it's overwhelming. So it's all good. It's all good. And if anyone is in San Antonio, please feel free to reach out to me. And this last slide is in dedication to my late supervisor, Harold. And I just wanted to share, so the interview that I had with him, I said after my master's, this is my last slide. So the interview that I had with Harold, I had a Skype interview with him as to whether I would go get this job. And I was kind of interviewing him back. So I was like, I don't know if I want to go to the Netherlands and like do a PhD. But anyways, he was interviewing me and he was looking at my CV and he was getting to the points where it showed, I was in a graduate program for 1 year and then I did industry. And most everybody, PhD supervisors, would ask me, okay, what happened at Emory? Like I saw you were there for 1 year. And so Harold was going through my CV and he got to that point and he was like, okay, so you were at Emory for 1 year. And I'm thinking, okay, he's going to ask the question that everybody asks. And he was like, and then you did industry. And I was like, yes, I did industry. And he asked, so which one did you like more? Did you like industry or did you like academia more? And I was like, I like academia more. I was pretty shocked. That was not the question I ever got from someone. And he said, okay, good. And then he just went along and asked me some other questions. And from that moment, it just made me realize that I was going to be with someone very seasoned and someone who's very open-minded and understanding. And so I'll always remember my time at Leiden. And if it wasn't for Harold, I wouldn't be here today. I learned a lot from him as a young professional. So I dedicate this talk to him. And thank you for having me, and thanks for sticking around.
Okay, I have a question.
Yeah.
This was very interesting. And you had at some point a grain that had absorbed some NH3 and some CH4. And I was thinking, you remove an hydrogen, you get an amine group. Then you have maybe a carboxyl group somewhere. You are pretty close to amino acids.
Mm-hmm.
So have you looked in your lab at the precise mechanism by which you move from those building blocks you described to something like an amino acid?
Yeah, like trying to understand the mechanism of how we make these amino acids.
Right.
Yeah, and we actually did that. There are different ways to make the amino acids. If you can make it like from simulate it in an asteroid, but we actually did make glycine, the simplest amino acid, just from atoms, which is pretty cool. And we made it under the interstellar dark cloud condition, which is just 10 Kelvin and no radiation. And so we found that you can actually make glycine, and we figured out that mechanism just from putting atoms and very reactive molecules together in the dark cloud.
Well, Stanley Miller did that years ago, but you seem to do that without any kind of extra energy like they had.
Yeah. So there's no we don't do any energetic processing. Like we don't add any radiation to making the amino acids.
Okay, Chris Shoemate, you had a question and a comment. You want to come off mute and ask Dr. Qasim?
Yes, certainly. Excellent presentation, Doctor. Really appreciated it very much. If we find ourselves over in San Antonio on some business trip or something like that, is there a good email or number that you could share that we could maybe contact and get signed up for a tour you'd mentioned earlier?
Yeah.
Do you mind if I share your email address? I can put that on the chat.
Yeah, I was
Would that
going to
work?
ask you if you could do that.
Yeah,
Thank you.
I'd be happy to.
And if I missed it earlier, I apologize. But
You also had no, I didn't put it on yet, Chris, I will. But you also had a question about OSIRIS-REx samples?
I did not.
Oh, I'm sorry. it's
Well,
Chris Summers.
I will have a
Chris Summers,
question
I'm
there.
sorry. All
I
right.
mean, the OSIRIS-REx has returned 14 of the 20 amino acids of life. I find that absolutely fascinating, and that's not all. They found all the 5 bases that are the basis of RNA and DNA. I mean, that's absolutely incredible. Tell us more about that.
Okay.
Yeah.
And Chris Summers, you want to jump in and ask your question real quick? I'm sorry, I thought it was Shoemate.
No, Daniel just answered it. So let's,
Oh, okay, that's fine.
yeah, let's go on. I want to hear more about that.
All right.
Yeah, well, sorry to disappoint. I don't know that much about the OSIRIS-REx samples, even though because I left, to SWIRI, and I worked with the OSIRIS-REx people before they collected the samples. But yeah, they found, I think, 5 nucleobases. It sounds like you probably know more than me actually about it. But I think they discovered like 5 nucleobases, which we did recreate in the lab, which is pretty cool. So a lot of the laboratory experiments that have been done formed the molecules that they detected. 5 nucleobases, and I think you said 14 of the amino acids. But I think one of the issues still is trying to understand the enantiomer. So I think it's either sugars or with the stereochemistry. So life is biased towards, I forget, is it left or right-handed? But it's like it's biased towards one conformer of sugar and one conformer of amino acids. And we still don't, in these extraterrestrial samples, like the ones from Bennu, we still see 50-50. So it's like a racemic mixture. So it's not the same as the composition that we see on Earth. And we're still trying to understand that. Like why do we see these, or like why do we see amino acids and components of RNA and DNA in space, and we get these samples, but they don't have the ratio that we have in life. So that's still a big mystery. But it's really cool to get these OSIRIS-REx samples because with meteorites, there's a lot of contamination with Earth. With just coming through, and I think one colleague is actually about to write a paper about how there's like spit on a lot of these meteorite samples, and so with OSIRIS-REx you get these like pristine, clean samples, and so you can eliminate a lot of the ambiguity that comes with analyzing meteorites. So that's as much as I can share about that.
Okay, Kenneth Draco, you had a comment and a question. Do you want to come off mute and ask Dr. Qasim? Well, Kenneth? Okay. Looks like he may not be exactly there. No microphone. I see. Okay. So I'll read your question then. I think Draco put in the chat. Your work sounds so much more advanced than that of Dr. Donald Clayton, PhD from the 60s to 90s. How familiar are you with the lifelong work of Dr. Clayton, Donald Clayton, on stardust, cosmic chemical memory, and survival rates of refractory stardust? Also, his textbook Principles of Stellar Evolution and Nuclear Synthesis. Are you familiar with that? Any of that, Dr. Qasim?
No, but I feel like I should be. I probably have seen work from Dr. Clayton. I just can't recall right now.
Okay. Well, and I think Kenneth also put on the chat that it's interesting that Dr. Clayton passed 3 days after your professor Linnartz. So kind of a coincidence there, I guess. With that, I'm going to take the privilege of asking the final question, if unless anybody else has got a question. And you know, in going through and looking at the interstellar, the interstellar medium, and studying that a little bit on my own, I understand that almost 250 different molecules have actually been discovered. And I'm just curious, how many, if I don't mean to put you on the spot, but what percentage of those do you think are phosphorated?
Yeah, not a lot. It's
Yeah,
mostly carbon, hydrogen, oxygen. I think phosphorus is, I forget the percentage. It's like probably less than 1%.
Yeah.
Yeah.
Okay.
It's hard because a lot of the phosphorus is also, the problem also is like a lot of phosphorus gets trapped in minerals. So, and a lot of these observations are in the gas phase. So they'll like probe it in the gas phase, but phosphorus and sulfur condense into minerals pretty early on, whereas like hydrogen and oxygen, they're all in the gas phase.
Yeah, it just seems like they're the phosphorus oriented molecules are so important to the life that it's kind of interesting that there are probably not that many of them. And you know, I think if you are successful in kind of bridging the gap between how they maybe got here to Earth, it could be a huge discovery. I mean, I know it's been really hard for a lot of years for researchers to come up with the exact steps on how life started, but boy, that would be a big one.
Yeah, thanks. Yeah, it's been pretty cool, like phosphorus and sulfur as well. Sulfur is just next door, and I don't know if you guys saw, there's like a picture from the Mars rover where it like ran through a bunch of sulfur crystals. It just saw a bunch of just ran over a bunch of sulfur crystals, which is pretty interesting because it shows the whole reservoir of sulfur trapped in the solid as we're expecting. So just gives us some clues as to where the sulfur and phosphorus is in other planets and moons.
Okay, thank you very much, and I really appreciate it. It's been really, for me, it's been very enlightening. I know for other folks on this call, it's been really enlightening discussion. And I just want to turn around and reciprocate your invite. You know, we're having this clash of the huge Dobsonian telescopes at the end of the month. If by any chance you're free and have some interest in actually going and looking through a big telescope, I'd be happy to make sure you got there. It just let me know offline. You don't have to answer now. But I just want to extend the invite if by any chance you're interested.
Thank you. Yeah, it was a huge honor. I really appreciate this opportunity.
Hey, Don, he says his hand up.
Okay.
All right. Well, thank you again.
Walt's got his hand up. I'm sorry.
Okay. Yes, Walt.
Is it too late to ask a question?
It's never too late for you, Walt.
Oh, gosh, thank you. Now, hey, so Dr. Qasim, I wanted to ask, you mentioned the asteroids, meteorites are salty. and that some of the groups that you've been studying are preserved in those salts. Could you say a couple more words about other kinds of salts? You know, there's plain old table salts and many, many more. What kind of salts do you mean when you say it's very salty?
Yeah, there's definitely, so there's the table salt like sodium chloride, but there's other salts, and it's interesting because there's sulfur salts, and so that's one of the big questions along with phosphorus is, where's all the sulfur being trapped as well, and where's all the phosphorus being trapped? And we're seeing a lot of sulfur bearing salts in Comet 67P. So it's like, I think ammonium NH4SH or something like that. There's also, I think, cyanide containing salts, magnesium sulfates. Yeah, lots of sulfur. Yep, there's salt on another asteroid, and Europa Clipper. So that mission, and the JUICE mission going to Europa. If you've seen like the tiger stripes on Europa, which is the moon of Jupiter, that has a lot of salts too, and it's it's a surprising number of sulfur in these salts.
Okay, thank you. And yes, to amplify Don's invitation, Saturday night, June 28th, it'd be fantastic if you could find your way to the dark side, and we'd love to show you all this stuff through the big telescopes.
Yeah, thank you. Yeah, I'd love to be more involved in HAS.
All right. Well, thank you very much. Thank you for being with us, Dr. Qasim. It was a wonderful, wonderful presentation. I'll see everybody next week. The meeting information's on the screen. Because of the July 4th holiday, next month's meetings will be a week later than usual on the second Thursday and Friday of the month. That's the novice meeting on July 10th and the general meeting on July 11th at 7 p.m. Be sure to visit our website for all the details, and be sure to hit us up on all the social media sites, Facebook, X, Instagram. Our YouTube channel has, of course, all the recordings of all the past meetings. Well, maybe not all of them, but every as many as we as we have. I mean, most of them are there. And if you need any further information, be sure to you can always email us at info@astronomyhouston.org. And with that, I will say good night and clear skies to all, and have a pleasant evening.
Thank you again.